Hello Math 116. So this is the video to make up for the class that we missed right before break on Tuesday. The goal for the video is just to cover section 5.2, which is what we would have done in class. And section 5.2 is all about sum and difference identities for trig functions, as well as some cofunction identities. So we'll talk about that too. But it's mainly devoted to these sum and difference identities. So let's get started. All right, so in this section, we're going to develop some more complicated trig identities than we've seen before. So all of the trig identities up until this point have kind of followed very quickly from the definition of the trig functions. So as we define the trig functions to be points on a unit circle, a lot of the identities, like the Pythagorean identities, the quotient identities, and so on, they all basically followed by definition, so we didn't really have to prove too much. But we're going to move into the realm of trig identities that are not so obvious anymore, and they're going to require some work for us to verify that they're actually true. So here's just an example of a couple of the identities that we're about to prove. So these are some sum and difference formulas, and specifically they're sum and difference formulas for cosine. So we end up with this identity, cosine of u plus v is equal to cosine u times cosine v minus sine u times sine v. And we also have a similar formula for the difference of two angles. So we have cosine u minus v is equal to cosine u times cosine v plus sine u times sine v. So right away, the first question you're probably going to ask is, do I have to actually memorize these identities? And my answer is going to be, no, you don't have to quite memorize them, but you should be familiar with the identities, and when you take the test, you're going to have the ability to write down these identities on a blank piece of paper if you want to, but you should be able to use them, and you should be familiar enough with the identities that when they pop up in practice, you should recognize them and be able to mess around with them. Okay, so again, these equations are identities, so the equations inside of the box here, they're true for any u and v you can possibly put in there. They're true all of the time. These things are always identical to one another, which is a little bit surprising if you haven't seen this type of thing before. All right, so let's try to understand why these two identities are true. So we're going to start out by considering the difference identity, which is the second one inside of the box. So this identity says that cosine of u minus v is equal to cosine u times cosine v plus sine u times sine v. All right, so let's start off by drawing a picture of what's going on here. So inside of this left picture, I have two angles. So I have the angle v, which is the smaller angle, and then I have an angle u, which is the bigger one. And you also have the angle that's made by these two. So you have the angle u minus v in between there. And I have a couple of points out on the unit circle. So I have the point P and I have the point Q out here. And the coordinates of those points are just going to be cosine u sine u or cosine v sine v respectively. So all of this picture kind of follows from definition of the trig functions. And we also have this second picture on the right. So to get this second picture, I'm taking that angle u minus v and I'm just rotating it so that I put it into standard position, right? So it's the same angle, the same size, u minus v, but we've just kind of rotated it clockwise so that it's in standard position now. And now I get these new points that are out on the unit circle. So I get this point B, which is cosine of u minus v, sine of u minus v. Those are the coordinates. This is, this follows by definition. And the point Q, when I rotate it, I'm rotating it down to this point A, which is just the point 1, 0. All right, so we get this second image by taking that angle u minus v and we rotate it over to standard position. All right, so how is this going to help us get this identity? Well, let's think about it a little bit. All right, so what do I know now? Because I'm rotating things and I'm not changing the length of any of these angles, this triangle made with the point PQ in the origin is going to be congruent. So this is congruent to the triangle made by the point B, the origin in A. That's coming from the second picture. So this is just saying that these two things are really the same triangle, And in particular, that means that if I look at the distance between the points P and Q from the first image, that has to be equal to the distance from the point B to the point A from picture 2. Because again, we're just rotating this angle. None of the distances are changing. All right, and if these two things are equal to one another, then if we square both sides, that's going to be equal to. So the distance between P and Q squared is equal to the distance between B and A squared. So this is true as well. But now let's take this formula on the right-hand side and let's rewrite this in terms of the coordinates of each of these points. So we're going to get a bunch of complicated stuff with cosines and sines. All right, so the distance formula looks like the square root of x2 minus x1 squared plus y2 minus y1 squared. That's how we get the distance between 2 points. And in this case, the x2, x1, y2, y1 are going to be cosine and sine in terms of u and v in various ways. All right, so if we look at the distance between p and q and we square it, we're just going to get rid of that radical sign, and we end up with a cosine u minus cosine v squared plus a sine u minus sine v squared. So this is what we're going to get from this distance between p and q squared. All right, and we know that this has to be equal to the distance between b and a. And if I use the distance formula between b and a, now I'm going to get cosine of u minus v minus 1 squared plus sine of u minus v minus 0 squared. And you should verify that I actually plugged in for the distance formula correctly here, but I really am just taking the components of each of these points in the picture and plugging them into the distance formula, and I get this equation that I know has to be true. All right, so let's take the left-hand side and let's simplify it and see what happens. All right, so we start with the left-hand side, and we're starting with cosine u minus cosine v squared plus sine u minus sine v squared. All right, so now I want to rewrite this and rewrite it as best I can to simplify it and make it look nicer. All right, so first we're going to take each of these squareds and we're going to move them through the difference in both cases. So we get a cosine squared u minus 2 times cosine u cosine v plus a cosine squared v. So that's from this first difference squared. And now we're going to get a plus sine squared u minus 2 sine u sine v plus sine squared v. And that's coming from this second difference squared. And now let's see if we can simplify it even more. So what do I see here? I see I have a cosine squared u plus a sine squared u inside of here. And then I also have a cosine squared v plus a sine squared v. So that's sitting inside of there. And now I have a minus 2 times cosine u cosine v and a minus 2 sine u sine v. So I also have that. All right, and now we can use the Pythagorean identity on this cosine squared u plus sine squared u and cosine squared v plus sine squared v. And that's going to give me a 1 plus a 1, so I get a 2 minus, and now the other guys just come along for the ride. So cosine u cosine v minus 2 sine u sine v. All right, and I have a factor of 2 in each of these terms here, so let's factor out that 2. And I get a 2 times 1 minus cosine u cosine v minus sine u sine v. So I took that left-hand side expression and now I rewrote it and simplified it a little bit to get this new expression. All right, now let's look at the right-hand side and see if I can simplify that too. So now I have cosine of u minus v minus 1 squared plus sine of u minus v minus 0 squared. And now I'm going to expand again, so I get a cosine squared of u minus v minus a 2 times cosine of u minus v plus a 1. So that's what I get when I expand the square of the first difference. And on the other side, I'm just going to get a sine squared of u minus v this time. All right, and now let's rewrite it again. So here I have a cosine squared of u minus v plus a sine squared of u minus v. And I also have a minus 2 cosine u minus v plus a 1. And the reason I'm rewriting it like this is because I have a Pythagorean identity sitting inside of there. So that's going to become 1, and I end up with 2 minus 2 times cosine u minus v when it's all said and done, and now I can factor out a 2. So I get 2 times 1 minus cosine of u minus v. Alright, so this is another way to rewrite the right-hand side, but the left-hand side and the right-hand side have to be equal to one another. So we have the following equation: 2 times 1 minus cosine u cosine v minus sine u sine v is equal to what we have for the right-hand side now, which is 2 times 1 minus cosine u minus v. Alright, now I can divide both sides by 2, and this is going to give me 1 minus cosine u cosine v minus sine u sine v is equal to 1 minus cosine of u minus v. So this is now true, and now the 1's are going to cancel. And so I'm just left, let's see, yeah, if I cancel the 1's, and then I multiply by a negative 1 on both sides, then I'm just going to be left with cosine u cosine v plus sine u sine v has to be equal to cosine of u minus v. So I have that this equation has to be true. And if we go back up to this original box, that is exactly what I wanted to show, this second equation. We've now proven that that equation has to be true. Alright, so that is definitely the longest proof that we're probably going to do in the entirety of the class. That's probably the most complicated thing. All of the other identities that we're going to get, they end up following much easier after we have this first one. So we can start getting other ones without as much trouble. Alright, so let's move on and get the sum identity too, so the other one that was inside of that box. Alright, so notice, if we want to look at cosine of u plus v, now that we have cosine of u minus v, well, instead of trying to do the whole thing again, let's just rewrite cosine of u plus v as cosine of u minus negative v, right? Because u minus negative v is the same as u plus v. And now let's use the formula that we just developed, because now I have something in the form u minus something else. Okay, so this is going to give me a cosine of u times a cosine of minus v, using this formula up here, plus a sine u times a sine of minus v. Okay, but remember that cosine and sine have these even and odd properties that give us some identities too. So if I look at cosine of minus v, that's showing up right here, that's the same as cosine of v, because cosine is an even function. And if I look at sine of minus v, that's going to give me a minus sine of v, because sine is an odd function. Alright, and now simplifying a little bit, we get cosine u cosine v, and now I get a minus sine u sine v. Alright, so at the end of the day, what we've shown is that now cosine of u plus v has to be equal to cosine u times cosine v minus sine u times sine v. So this was the second equation that showed up inside of this box that I had written out here at the beginning. So now we have two new identities that we can use for cosine. If you have the cosine of the sum of two things or the difference of two things, you can rewrite it in this way. Alright, so next up, let's take these identities that we now have for cosine of the sum and difference of angles, and let's apply them to some different examples to show why we might be interested in this in the first place. Alright, so in this first example, we want to find the exact value of cosine of pi over 12 by using the fact that pi over 12 is equal to pi over 3 minus pi over 4. Alright, so it's important to notice that pi over 12, this angle that we're referring to, is not one of the angles appearing on our typical unit circle. In other words, it's not one of the angles that we are very familiar with, where we can just kind of write down what cosine of pi over 12 has to be. So if we want an exact answer, we're going to have to work a little bit harder. All right, but we do know that cosine of pi over 12 has to be equal to cosine of pi over 3 minus pi over 4, because pi over 3 minus pi over 4 is just equal to pi over 12. But now we can rewrite this with our difference formula that we just found for cosine. So this is going to give a cosine of pi over 3 times a cosine of pi over 4 plus a sine of pi over 3 times a sine of pi over 4. So this is just applying the difference formula that we have for cosine. And again, maybe you don't have that memorized, but you can have that written down, and as long as you're able to use it like this, that's fine. All right, so now we've rewritten it in terms of cosines and sines of angles that we are familiar with. So all of these angles are sitting on the unit circle, so I should know what cosine and sine are at each of these angles. So cosine at pi over 3 is going to be a 1/2. Cosine at pi over 4 is root 2 over 2. Let's see, sine of pi over 3 is going to give me a root 3 over 2. And sine of pi over 4 is a root 2 over 2. So these values you should know just from using the unit circle. So maybe you would need to stop and draw a unit circle or something to get your bearings, but you should be able to figure out these values without using any kind of calculator or additional help. All right, so now 1/2 times root 2 over 2 is going to give us a root 2 over 4, and root 3 over 2 times root 2 over 2 gives a root 6 over 4. And now we just add them together, and we get root 2 plus root 6 over 4. So this is the exact value of cosine of pi over 12, and we found it by using this difference formula that we've developed now. Okay, in the next example, we show that you can also use the sum or difference formulas when you have angles in terms of degrees as opposed to radians. Nothing really changes here. So this time, we have that cosine of 75 degrees is equal to cosine of 45 degrees plus 30 degrees, because 75 is equal to 45 plus 30. But now we can use our sum identity for cosine, and we get cosine of 45 degrees times cosine of 30 degrees minus sine of 45 degrees times sine of 30 degrees, just by plugging this in to the sum formula for cosine. And now we have everything written in terms of angles on our unit circle. So we should understand all of these values that are showing up here. Cosine of 45 gives me a root 2 over 2. Cosine of 30 gives me a root 3 over 2. Sine of 45 gives me a root 2 over 2. And sine of 30 gives me a 1/2. So now I'm going to end up with a root 6 over 4 minus a root 2 over 4. And now I'll simplify and get root 6 minus root 2 over 4. So this is the exact value for cosine of 75 degrees, and we found it by using this sum formula that we now have for cosine. Okay, so now that we have this sum and difference formula for cosine, let's move on to talking about some different identities, and then eventually we're going to come back to sum and difference formulas for sine as well. So these next identities are called cofunction identities by the book. To be honest, I've never heard this term cofunction identity, but that's what we're going to refer to them as from now on. All right, so we're going to develop just a few more identities that we can use. And so we already have from the first part that cosine of u minus v is equal to cosine of u times cosine v plus sine u times sine v. So what happens if we take this formula that we already have and we let u equal pi over 2? So if we do that, we get cosine of pi over 2 minus v is equal to, and now let's plug it into the right-hand side of our difference equation. we get cosine of pi over 2 times cosine of v, and then we have a plus sine of pi over 2 times sine of v. Okay, but cosine of pi over 2 is just going to be 0, and sine of pi over 2 is just 1. So the left-hand part of the sum is going to end up being a 0, and the right-hand part of the sum is just going to be sine of v. So this gives us another identity that we have. So for all v, cosine of pi over 2 minus v is equal to sine of v. So this is true all the time. It's another identity that we can now use. All right, but we can do the same kind of game in the opposite direction. This time, let's take this, this new identity that we have, and we're going to specify that v is equal to pi over 2 minus u for any u. And now, if we play the same kind of game, we have cosine of pi over 2 minus pi over 2 minus u. So we substituted that in for v, and this is going to give us a cosine of, yes, just a cosine of u, but using the previous formula, this is also going to be sine of pi over 2 minus u. Okay, so this tells us that sine of pi over 2 minus v is equal to cosine of v for all v. So we've just kind of done a trick here, switching the different variables between v and u, but we have this new identity too. And both of these identities are examples of cofunction identities. All right, so for our next example, let's verify another cofunction identity, the identity that states tangent of pi over 2 minus v is equal to cotangent of v. All right, so we're going to start with the left-hand side. Whoops, I want this to be black. So we start with the left-hand side, and we work our way to the right-hand side. So we have tangent of pi over 2 minus v, but we can use the quotient identity here, and this is sine of pi over 2 minus v over cosine of pi over 2 minus v. And now we can use the cofunction identities that we already have. So sine of pi over 2 minus v is just equal to cosine of v, and cosine of pi over 2 minus v is just equal to sine of v. And now again, using the quotient identity, this is the same as cotangent of v. So now we've derived this next cofunction identity, tangent of pi over 2 minus v is equal to cotangent of v. And we can do these same kind of arguments again and again to get the following 6 identities, which are all called cofunction identities. So we have cosine of pi over 2 minus v is equal to sine v, sine of pi over 2 minus v is equal to cosine v, tangent of pi over 2 minus v is equal to cotangent v, and then we have some similar ones on this side that relate secant, cosecant, cosecant and secant, and then cotangent and tangent on the right-hand side. So why are these called the cofunction identities? Well, notice that in each of the equations we have kind of co-functions on either side. So what do I mean by that? Well, notice that sine and cosine are related in these equations here, and secant and cosecant are related in these equations, and then finally tangent and cotangent. So we have this identity that relates a function of pi over 2 minus v, and then the function of v, and it relates the function with its cofunction. So this is why we get the name cofunction identities. All right, so the natural next question to ask is, if we have these sum and difference identities for cosine, shouldn't we also have sum and difference identities for sine as well? And the answer ends up being yes. And fortunately, we don't have to work as hard for these identities as we did for the cosine identities, because we can use the cosine identities as well as the cofunction identities to derive these identities for the difference in sum of sine. All right, so let's look at sine of u minus v, and we want to get some kind of identity that we can put on the right-hand side of this equation here. All right, so the first thing is that sine of u minus v has to be equal to cosine of pi over 2 minus u minus v. So this is one of the cofunction identities that we have. And from here, we can rewrite this as cosine of pi over 2 minus u plus v. And now let's use our formula that we have for the addition of angles and cosine. So this is going to give us a cosine of pi over 2 minus u times a cosine v minus sine of pi over 2 minus u times sine v. And again, this is the formula that we have for the addition of angles inside of the cosine function that we developed at the beginning. But finally, we can use the cofunction identities again. So cosine of pi over 2 minus u is now going to become sine u, cosine v stays the same, and sine of pi over 2 minus u becomes cosine u, and sine of v stays the same here. So now we have a formula for sine of u minus v. So sine of u minus v is always equal to sine u times cosine v minus cosine u times sine v. So this is another formula that you should not necessarily memorize, but be familiar with and have it written down and know how to apply. So now we have sine of the difference of two angles. We can also talk about sine of the sum of two angles. So to get this, sine of u plus v is the same as sine of u minus negative v. And now we can use this formula that we just got for sine of the difference of two angles. And we get sine of u times cosine of negative v minus cosine u times sine of negative v. And now we do this similar trick that we did for cosine, where we recognize that cosine and sine are either even or odd functions to pull these negatives out. All right, so first off, cosine of negative v is the same as just cosine v, because cosine is an even function. And sine of negative v is going to give us a minus sine of v. And now simplifying, I get sine u times cosine v plus cosine u times sine v. So this gives us our identity for sine of the sum of two angles. We get sine of u plus v is always equal to sine u times cosine v plus cosine u times sine v. All right, and so I took both of these formulas that we now have derived and I just put them inside of this box so that you can refer to it pretty easily. So these are our sum and difference formulas for the sine function now. Okay, so let's take these sum and difference formulas for sine and let's put them into action and do some stuff with them. So we'll calculate a few different examples. So in this first one, we want to prove this new identity that says sine of pi minus x is always equal to sine x. All right, so let's try and verify that this is in fact an identity. So we're going to start on the left-hand side with sine of pi minus x. And now I'm going to use this difference formula that we have for sine. So sine of pi minus x is equal to sine of pi times cosine of x minus cosine of pi times sine x. All right, now let's see what happens. So sine of pi is just 0, and cosine of pi is negative 1. So the first part of this sum, the sine pi times cosine x, just gives us a 0, and we have exactly 1 sine x coming from the second part of this sum. So now we've shown that sine of pi minus x is always equal to sine of x by using this difference formula for sine. All right, another type of example we can do. In this case, we want to find sine of 63 degrees times cosine of 27 degrees plus cosine of 63 degrees times sine of 27 degrees, and we want to do it without using a calculator. So the key thing to notice here is that this looks an awful lot like the second hand or the right-hand side of this formula for sine of u plus v. So sine of 63 degrees times cosine of 27 degrees plus cosine of 63 degrees times sine of 27 degrees is going to be equal to sine of 63 degrees plus 27 degrees. So we're kind of using the sum formula for sine, but we're going in the opposite direction now. we have something that looks like the right-hand side of this equation for sine of u plus v, and we're rewriting it as sine of u plus v. So we get this sine of 63 plus 27, but now sine of 63 plus 27 is just sine of 90 degrees, and sine of 90 degrees is just 1. So this thing that we started with, sine of 63 times cosine of 27 plus cosine of 63 times sine 27, is actually just equal to 1, and we could figure that out without having to use a calculator. All right, so next up, we want to verify this identity that says sine of x minus y over cosine x cosine y is equal to tangent x minus tangent y. And again, we're going to use this formula that we have for the difference of two angles inside of the sine function. So we have sine of x minus y over cosine x times cosine y. This is what we're starting with, and we're trying to make it look like the right-hand side of this equation. So we're going to use the difference formula for the top here, and we get sine x times cosine y minus cosine x times sine y on the top. And the cosine x times cosine y, that's going to stay the same on the bottom here. Okay, and now we can factor this cosine x cosine y through each of the terms of the difference in the numerator. So we get sine x cosine y over cosine x cosine y minus cosine x sine y over cosine x cosine y. So we split up that difference now. And now we can simplify a little bit more. So this cosine y and the cosine y on the bottom are going to cancel with one another. And we're just left with a sine x over cosine x here. And in this second fraction, we have a cosine x and a cosine x that are going to cancel with one another. So we're just left with sine y over cosine y. But now, by the quotient formula, this is just tangent x minus tangent y. So this last part is just by the quotient identity for tangent. So we've proven this identity that we have for sine x minus y over cosine x cosine y. Okay, so finally, we've talked about sum and difference formulas for sine and cosine. You might ask, can we also get identities for the sum and difference of angles with the tangent function as opposed to just sine and cosine? And again, the answer ends up being yes, and we don't have to work as hard as we did for the cosine function because we can use the identities that we already have to prove this new identity. All right, so we're going to start out with tangent of u minus v, and let's see if we can rewrite this and get something else. So the first thing I notice is that tangent of u minus v can be rewritten as sine of u minus v over cosine of u minus v. So this is the quotient identity. But now we have formulas for both of these things in the numerator and the denominator. So sine of u minus v, we found out is the same as sine u times cosine v minus cosine u times sine v. So that's the difference of angles for sine. And we also have the difference of angles for cosine. This is going to give us cosine u times cosine v plus sine u times sine v. So we can rewrite tangent of u minus v in this way. And now there's this kind of strange manipulation that we can do algebraically. We can take the top and the bottom, and we can multiply by 1 over cosine u times cosine v. So this seems a little bit strange or arbitrary, but it's going to end up simplifying down nicely. So we multiply everything inside of this expression by 1 over cosine u times cosine v. And we end up with this expression with a bunch of different fractions. So here's just the numerator that we've now multiplied by 1 over cosine u cosine v. And the denominator, we get cosine u cosine v over cosine u cosine v plus sine u sine v over cosine u cosine v. Okay, and the reason that we're doing this is because we have a lot of simplification that happens then. So in the numerator, we have this cosine v and cosine v. They're going to cancel with one another. we have a cosine u and a cosine u that cancel with one another. In the denominator, this is just 1, that first fraction. And secondly, we can think of this second fraction as sine u cosine u times sine x, or times sine v cosine v. Okay, so what does this allow us to say? In the top, we're now just left with sine u cosine u minus sine v over cosine v. And on the bottom, we just have a 1 plus, and now we have a sine u over cosine u times a sine v over cosine v. All right, and we can simplify this, and we just get a tangent of u minus a tangent of v in the top. And in the bottom, we get a tangent of u times tangent of v. So now we've taken this expression that we had, tangent of u minus v, the difference of angles, and we've rewritten it using just tangent, and just evaluating tangent at the angles u and v and putting them together in some nice way. So this is our new identity for the difference of angles with tangent. Okay, and just like we did with sine and cosine, we can also then figure out what's tangent of u plus v. So we rewrite tangent of u plus v as tangent of u minus negative v, and now use the identity that we just got. So we get tangent of u minus tangent of negative v over 1 plus tangent of u times tangent of negative v. But remember, tangent is an odd function. So we rewrite this as tangent of u plus tangent of v over 1 minus tangent u tangent v. And this now gives us our formula for the sum of angles inside of the tangent function. All right, so I took both of those formulas that we now derived and I put them inside of a box for you, so that you now know tangent of u plus v is equal to this thing, tangent of u minus v is equal to this thing. And again, you don't have to memorize these things, but you should write them down somewhere for the test and then have the ability to use them when you need to. All right, so the last example we're going to do, using the sum or difference formulas of tangent now, we want to verify the identity that says that tangent of pi minus x is equal to negative tangent x. All right, so we have tangent of pi minus x is equal to, now we're going to use the difference formula, and we get tangent pi minus tangent x over 1 plus tangent pi times tangent x. All right, let's see if we can simplify this. So tangent of pi, because sine is equal to 0 at pi, tangent of pi is just going to be 0 in both of these cases. And so we're just left with a minus tangent x over 1, which is just minus tangent x. So we've proven this identity now that tangent of pi minus x is equal to minus tangent of x. All right, and then finally, I just took all of these different identities that we've derived throughout this video and in this section and put them into some boxes here so that it's very easy for you to reference when you're going through the homework. So ultimately, again, you should not necessarily memorize these things, but you should have familiarity with them and you should have them written down when you take the test and be able to use them to prove some different trig identities and use them on the homework. All right, so I'll see you in class after break.